computer. At the end properly, right?
Mhm.
Yeah?
Yep.
All right, cool. So the only trigonometry, the only trig video you will ever need, or the trig class you'll ever need in your life. Now, when we talk about trigs in advanced, we need to have the knowledge for trigs in maths. And trigs in maths says that if I have, let me say, cosine of some angle theta, and cosine of an angle, let me say it's equal to 1/2. How do we calculate the value of theta? Go ahead. Ask some question.
Cosine inverse of a half.
Cosine inverse of a half.
Yeah.
Cosine inverse of 1/2. So let me jump on the calculator here. I have cosine inverse of open bracket 1 divided by 2 close bracket.
60.
And we get 60 degrees. Now this means that cosine of 60 degrees is equal to 1/2. And they're the only angle we tried to solve for when we were doing basic trigs with right angle triangles or non-right angle triangles. But something else happens. If I give you a task and I say, Joshua, check and tell me what is cosine of 300. Check it and tell me. What did you get?
A half.
A half. So why didn't I get 300 as another angle when I typed in cosine inverse of 1/2? Because by all means, this is true. We now prove that it is true. Cosine of 300 degrees is also 1/2. So I could argue the fact that cosine inverse of 1/2 is also 300 degrees. Question mark. I just now did it on my calculator and I could do it again. Cosine inverse of a half, which is 0.5, is 60. Where does this 300 come from? I'll give you another task. What is cosine of, let's say, 420? Check it out, tell me.
A half as well.
Cosine of 420 is indeed a half. Where does these angles come from? Where? Very interesting. Right? Food for thought so far. Suppose I now have cosine inverse of the same thing, cosine theta is equal to -1/2. Now, same thing works for sine and tangent as well, right? I just decided to pick cosine. All right, so just for some variation, I will say if sine of theta is equal to 1/2, what is theta? It's sine inverse of 1/2. And what did you get?
Oh, wow. 8.2 to 1 decimal place.
Right, so let me use a
8.7 to 1 decimal place.
Let me use 1/√2, right? Just to make life a little bit easier. All right.
0.01 to 2 decimal places.
Sine inverse of 1/√2.
Oh, sine inverse. Okay.
I want to check and see, because I know sine inverse of 1/2 is supposed to be 30 degrees. It is 30 degrees. So we'll look with the half, right?
Right.
So theta is equal to 30 degrees. Yeah?
Yeah.
Now, this indeed means that, cosine of 30 degrees is equal to 1/2. Yeah?
Mm-hmm.
And sine of 30 degrees. But check this one now. What about sine of 150 degrees? What is that equal to?
Also a half.
Also a half. So you're telling me that our sine of 150 degrees is also equal to 1/2. Yeah?
Mm-hmm.
Which means, if calculations are correct, sine inverse of 1/2 is also equal to 150 degrees. But on the calculator, we didn't get its value. Yeah?
Mm-hmm.
Now you might be thinking, and everything I use in a half. What is the deal with that? Does it only work for a half? The answer is no. What about if I say tan of theta is equal to 1? What is theta? Wouldn't it be tan inverse of 1?
Yeah.
And theta will be equal to, if I'm correct,
45.
What about tan of 225 degrees? What is that?
Also 1.
That is equal to 1, which means to tell me that yet again, I end up with a similar situation where I have more than one angle satisfying a trigonometric equation. Yeah? Because remember, when we're solving these things, I'm solving for the value of theta that makes this equation equal to a half. For cosine theta, for sine theta, and for tan theta, I'm solving for the value of theta that makes tan theta equal to 1. But what based on the calculators, the calculator only gives us one answer. Yeah? I want to throw one more in the mix here. Negative.
Yeah.
What if I tell you that, and there's a reason I am picking a half, 1, and there's a reason I'll pick this value as well. Cosine theta is equal to negative √3/2. There's a particular reason I'm picking these values, and the reasons will be clear in a minute. What is theta?
Give me an error.
No, you wouldn't get error. Based on, put √2 in brackets. I mean, if I learn anything from before, theta will be cosine inverse of minus √3/2. Yeah?
Yeah.
So if I plug that in my calculator, cosine inverse, open bracket, negative √3/2, close bracket. Okay, 150 degrees. That is equal to 150 degrees. Now, if I tell you this one now, sorry, cosine of, let me say, 30 degrees. No, not 30 degrees. Let me use cosine of 30, I had 30 there, 150. No, we have that already, cosine of 150. Cosine of, so it will be 30, and 180 is 210. Cosine of 210.
Minus √3 and 2.
Minus √3 and 2. So it comes down to the question of, if I can do it, why can't you? Yeah? So we're going to learn how to do these things and why it is that more than one angle satisfies a trigonometric equation. So before we do that, we need to learn about what does trigs do to numbers wherever we have numbers. So let me ask you a question here. On your calculator, and I'll do it as well here. Pick an angle between 0 and 360 degrees.
162.
162. Pick a trig function, sine, cosine, or tan.
Cosine.
So we're calculating cosine of 162 degrees. Yeah? Now, in my head, I can tell you the nature of this number. This number is going to be a negative number.
Yes, it is.
Yeah?
Yeah.
So if I do so, it's going to be a negative number. Pick another angle and another trig ratio.
352.
Which one?
And tan of 352.
Tan of 352. I can tell you that this is going to be negative as well.
These are quadrants. These will appear in quadrants. Yeah.
As proven, it is a negative number. Yeah. So just like you said, it involves use of quadrants. Now, what is a quadrant? And how are we going to use the quadrants to determine what value is positive where and what value is negative where? So with quadrants, they make up the XY axis. Yeah?
Right.
And in each of these 4 pieces, the XY axis separated into 4 pieces, each of these quadrants, these 3 trigonometric ratios or identities, they behave differently. Now, we're going to prove what is positive and what is negative in each quadrant and try and figure out an innovative way to remember which is negative and which is positive. So we're going back to the long time days of trigonometry, right angle triangles. So I'm going to construct this right angle triangle in quadrant 1. Now in quadrant 1, we need to know this is my positive x-axis. This is my positive y-axis. This is my negative x-axis and my negative y-axis. This is a right angle here. Now, generally, all lengths are positive, but for use in this proof, I'm going to represent the lengths based on what axis the length falls on. So for example, if this is my angle theta, this will be my opposite. Agreed?
Mm-hmm.
This is my adjacent, and this is my hypotenuse. Correct?
Yes.
My adjacent is what type of number? Positive or negative?
It'd be a positive number.
Because it's on the positive x-axis. Yeah?
Mm-hmm.
My opposite will be a?
Also a positive.
And my hypotenuse, by using Pythagoras' theorem, what's going to be my hypotenuse?
Should be a positive number.
It's going to be a positive. Okay?
Yeah.
Let's check and see how the trig ratios behave in this quadrant. For reference, this is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4. So let me see how the trig ratios behave in each quadrant. Well, I know from long time, sine of theta is opposite over hypotenuse. This is a positive over a positive, which is going to yield
a positive value. Yeah.
Same thing for cosine of theta. It's adjacent over hypotenuse, which is also a positive over a positive, which will also yield a positive. And finally, tan of theta is a positive over a positive, which will also yield a positive answer. Now, if observation tells us anything, between the x positive and the y positive axis, I am between 0 degrees and 90 degrees. Because that angle, theta works in a counterclockwise direction from here to here. So if theta is increasing, I'm going from positive x-axis to the positive y-axis. It makes a right angle. Yeah?
Yeah.
Now, as we count the quadrants, the size of the angle persists in each quadrant. So in quadrant 2, I'll be between 90 and 180. In quadrant 3, I'll be between 180 and 270. And in quadrant 4, I'll be between 270 and 360.
360, yeah, that makes sense.
So if it is, I ask you, and you can check it on a calculator, any value between 0 and 90 degrees,
it should yield a positive value.
Will always be a positive value every single time. And you could check it on the calculator and see if you want to.
Okay.
Let me see what happens in quadrant 2. Same right angle triangle. Right? This is my right angle here. Again, I'm using theta. Theta is always measured with reference to the x-axis, always. All right? Opposite. Opposite is going to be what type of number?
It will also be a positive.
Adjacent going to be what type of number?
It will be a negative since it's on the negative x-axis.
And the hypotenuse
should be a negative since it's increasing negatively.
Sure. Check it by using Pythagoras' theorem. I have opposite squared plus adjacent squared is
using
hypotenuse.
Using Pythagoras would prove that if anything is squared, it usually yields a positive. So that means in all 4 quadrants, the hypotenuse should be positive, right?
Right.
That will make sense. Yeah, that would make sense. Yeah.
All right. So a positive number to be squared will be a positive, and a negative number to be squared will also be a positive. I have a positive plus a positive will always yield a positive number from my hypotenuse.
Yeah.
Right? Now, yet again, let me see what happens to the trig ratios in this quadrant. So sine theta, I'm not going to write its opposite over hypotenuse again, because we know it's opposite over hypotenuse. The opposite is positive, and the hypotenuse is positive. So that will yield a positive answer.
value. Yeah.
Right, so I can rub this off for now. I'll do cosine theta above it. Cosine is adjacent over hypotenuse, which will yield a negative answer. And tan theta is equal to opposite over adjacent, which will yield a negative answer. And just for proving its sake, remember, quadrant 2 is between 90 degrees and 180 degrees.
Yeah.
So if I were to check any of these angles, let's check cosine. Let me pick a number between 90 and 180. Let me pick 100. Yeah?
Mm-hmm.
If theta is between 90 and 180, cosine theta will be negative. It's negative. What about sine of 100? Will that be negative or positive?
It should be positive.
It will be positive. And tan of 100 will be?
Negative.
It will be negative. Yeah? And these are the concepts I'm going to use in every single quadrant. So I'll just make this triangle a little bigger, just so that we don't get confused with the triangle above it. Theta adjacent is going to stay the same place. It's going to be a negative number. My opposite is going to be what type of number?
Opposite should be a negative number. Yeah.
Negative number, because it goes down the negative axis. And my hypotenuse is going to be a
positive number, as always.
Before, it's always going to be positive. Again, sine theta is equal to opposite over hypotenuse, which will going to give me a negative number. Yeah?
Mm-hmm.
Cosine of theta, sorry, is equal to adjacent over hypotenuse, which is going to give me a negative number. And tan theta is opposite over adjacent, which is going to give
positive value.
So we can check it again. As stated again before, in quadrant 3, that's between 180 degrees and 270 degrees. So let me just pick a weird angle to work with, right? Let me pick 265. Yeah? Let me pick 252.3. Right? A weird number to work with. Sine of 252.3 should give me a negative number.
Yeah.
It will give me a negative number. Cosine of 252.3 will also give me a negative number, but tan of 252.3 supposed to give me a positive. It does give me a positive value. And finally, in the last quadrant, like I said, I'll draw the triangle a little bit bigger to avoid confusion. Right, so I will just complete it freehand, right? This is theta, adjacent remains the same. This is my opposite, which will be a negative, and my hypotenuse, which is going to be a positive
value.
So let me see. Sine of theta is opposite over hypotenuse,
which will yield a negative value.
Cosine of theta is equal to adjacent over hypotenuse, which will yield a positive value. And tan of theta is equal to opposite over adjacent, which will give me a negative value. Yeah?
Mm-hmm.
Now, we could test it again and see. Quadrant 4 is between 270 and 360 degrees. So we can test it and see. Between 270 and 360, 299.
Yeah, sure.
Sine of 299 should give me a negative value. It does. Cosine of 299 should give me a positive value. It does. And
no, it
tan of
well,
299, it does. Which cosine of 299 is equal to positive.
No, oh, right, positive, right.
Positive. And tan of 299 will give me a negative value, as expected. Now, these things are expected. Now, observing the quadrants, it's a bit tedious now, because I have to try to figure out how am I going to remember all of this?
Actually, there's a good connection, because only one of these are negative or positive in quadrants 2 to 4. Well, one of them is negative sorry, positive, and the other two are usually negative, right? There's a trend here. It's definitely a sequence. So in quadrant 1, everything is positive. Quadrant 2, only sine is positive. Then quadrant 3, you have tan as positive. Tan of theta is positive only, right? And the other two ratios are negative. And then cosine in your fourth quadrant is only positive, I believe, and the other two ratios are negative.
Very good. Very good observation. So in each of these quadrants, 1, 2, 3, and 4, there exists a pattern, and the pattern emerges for positive values. So in the first quadrant, all are positive. Yeah?
Yeah.
In the second quadrant, sine alone is positive. Sine alone. In the third quadrant, tan is positive. And in the last quadrant, cosine is positive. And there's a little acronym that we use to try to remember which of these are positive where. And the acronym is all, I'll do it in a different color, all school teachers cos. And each of the letters in the acronym will represent that ratio, which is positive in that quadrant. So when you say all school teachers cost, that is the easiest way to remember it because it's so cliche. All means all are positive. School for S means sine is positive. T in teachers means tan is positive. And C in cost means cosine is positive. And it's a nifty way to remember it. But so far, all I learn is what is positive where. I learn how to get 300 and 150 and 225 and 210 as it. So where does this come from? In order to know that, we have to understand the quadrants properly. So from the quadrants, we're still focusing on quadrants a bit. From our quadrants, we have each of the angles being positive in, not the angles, each of the ratios, one of the ratios being positive in 2, 3, and 4, and all being positive in 1. Now, whenever we are doing calculations regarding trigs, we have actually an infinite number of solutions. And the reason we have an infinite number of solutions is because of how the trigs behave graphically. If I were to dive into GeoGebra and I draw, Jesus Christ, right, and I draw y is equal to sine of x, I get this. So just as how I draw y is equal to x squared, y is equal to a straight line, y is equal to a polynomial, there is a graph for y is equal to cosine x, sine x, and tan x. Now, I'll hide this for now. Long time, if we had y is equal to some straight line, 2x plus 6, and I ask you, I say, well, what is the value of y when x is minus 2? Well, I'll go on my x-axis, I'll look for minus 2, I'll go up and I'll see where minus 2 touches the graph, and I'll read the corresponding y coordinate. Yeah? I mean, the same thing we did when we had y is equal to something like, let me go with a simple x squared. I'll ask again, what is y when x is equal to 1? Well, I'll go up and I'll go across and I'll get a value for 1. Yeah? Now, the same thing happens, and we have to do the same thing here. Now, my axis is in terms of numbers, which is no problem at all. But can you see, just like in the quadratic, when x is equal to 1, y is 1. Also, there's another solution. When x is minus 1, y is also 1. Yeah?
Yeah.
When x is 2 or minus 2, y is 4. Yeah?
Yep.
So 2 values of x gives me 1 value of y. Yeah?
With respect to the quadratic, since it's x squared.
Quadratics. For trig graphs, there are a number of values of x, which gives me one particular value of y. So let me just change the axes. X-axis. Let's look in degrees, which is not really ideal. Let's look in radians. Good. Now, radian measure is a different type of way to measure angle, just like how we have meters, centimeters, kilometers, and stuff to measure distances. We have grams, kilograms to measure weights. We have a different unit to measure angles. Now, if all of these represent numbers, right? Pi is a number, 3.14.
Yeah.
Let me just pretend that this value here, right? And I'll be pretending to be realistic as well. This value, this x value here is 90 degrees. And I ask you, I say, what is y when x is 90 degrees? Well, you'll tell me, well, I'll go up and I'll go across and I get y is 1, correct?
Yes.
Similar to this, I'll go up, I will, we know this is 2, minus 2, yeah? We know that minus 2, right? Now, if I stem from 4 and I keep going, I can see, well, you know, this x value down here will also give me a y value of 4. Yeah? Same thing for same thing for 1.
Graph.
If I keep going across, I get this value and this value. Those two values will give me a y value of 1.
Right.
Yeah?
Mm-hmm.
If I work in the same frame of mind for my trig graph, and I want to know, well, how much values actually gives me 90 degrees or something like 90 degrees. But if I keep going across, shucks, I can see, well, you know, this value here, wherever this value is, also gives me a y value of 1. Go across here. This value, again, whatever he is, when I go up and I go across, I get a y value of 1. Yeah? And the sine curve, looking like it keep on going on and on and on and on.
It's infinite. It's an infinite series.
It never stops.
Right.
It never ever ends.
Neither does a line, technically a straight line.
Which makes me wonder, how am I going to calculate these other values of theta from watching a calculation? For example, up here, my graph directly correlates to my quadrants. And it works for all trig curves. All trig curves or trigonometric graphs are called cyclic, meaning they repeat themselves after a certain number of degrees. So every 360 degrees, which is, in this case, is 2 pi, and we'll get to the pi just now. 360 degrees is the same thing as 2 pi. Every 360 degrees, my graph repeats itself. So in the first 360 degrees, this is my graph. It's going up, it's going down, and it's stopping on my x-axis. Then it does the same thing again. It goes up, it goes down, and it stops at the x-axis. Then it does the same thing again. It goes up and goes down, and then it will stop at the x-axis in both directions. The cosine curve behaves the same way, and the tan curve behaves the same way. After a given number of degrees, brother man going and repeat himself, and repeat himself, and repeat himself. If I make that direct comparison to quadrants, this is what happens. From here to here is how much degrees?
A full 360.
Full 360.
Right.
Compare that to one cycle. Yeah? To one cycle. Cool? So start is 0 and end is 360. Yeah?
Yeah.
That's in cycle 1. In cycle 2, I'll start at 360. And where will I end?
720.
I'll end at 720. And I'll go again, and go again, and go again. Yeah?
Yeah.
Each of these cycles is called a revolution.
Okay.
So I have my first revolution, I have my second revolution, I have my third revolution, fourth, fifth, sixth, going down the road. Okay? I have an infinite number of revolutions. Cool. Very good concept to think about for now. I will get to the revolutions just now. Generally, in my first quadrant, theta is equal to theta. All right? Bear with me for now. We call an angle something called a principal value. And we'll learn what the principal value is just now. In the second quadrant, theta is 180 degrees. Take away the principal value. In the third quadrant, theta is 180 degrees plus the principal value. And in the last quadrant, theta is 360 degrees. Take away the principal value. What is this principal value business? The principal value will come if sine of theta is equal to k. Where k is some number, theta is some number. All right? My principal value is going to be sine inverse the modulus of k, where the modulus will take all positive values of k. So if k is a negative number, the principal value is going to be sine inverse of k, where k is positive. So if I give you an example, and I'll use the same one we have from above, sine theta is a half. If sine theta is equal to a half, my principal value is going to be sine inverse of a half. If sine theta is equal to negative a half, my principal value is going to be sine inverse the modulus of negative a half, which will be sine inverse of a half. Okay? Now, the only time you really use the modular signs is if you have a negative number there. All right? That's the only time you realistically use it or apply the modulus function. Now, by all means, we just now did this sine inverse of a half, brother man, is 30 degrees. Yeah? It was indeed 30 degrees. A couple things you have to look out for when you are solving a trig equation. The first thing you ask yourself, well, what is the trig equation? What is it equal to? What is sine theta equal to? In this case, it's very vague. I want a vague answer. What is sine theta equal to?
K.
Huh?
K.
No,
for the modulus.
in the example.
As in a half?
Over here. Here.
Sine theta is equal to a half here.
I want a different answer than that. What is sine theta equal to?
A number.
Keep going.
A positive number.
A positive number. Yeah, very, very, very important. That gives me information. And that information given to me indicates where theta is going to be found. Remember, I do have angles that will give me negative values for sine of theta. Yeah? Sine of theta is positive where?
It could be two places.
Where? I'm asking where?
It could be in either quadrant 1, I believe, and quadrant 2.
Or quadrant 2, not and. Or.
Okay.
Either or.
Right.
So based on the proofs, brother man, we proved that sine theta is a positive number and sine theta is a positive number in these two quadrants. Correct?
Yes.
So sine theta, I'll drop my little mini quadrant here. My principal value is something you have to calculate all the time, is equal to 30 degrees. Yeah?
Yeah.
Wherever you figure out where the angles are located, just parallel tick by them. It's in quadrant 1 and in quadrant 2. Cool? Now it's time to determine what the values of theta is. Well, I know in quadrant 1, theta is my principal value, which is indeed 30 degrees. And in quadrant 2, theta is 180 degrees, take away the principal value, which is 180 degrees, take away 30 degrees, which is equal to 150 degrees.
Yeah.
Now, if I check, I'll go back. For sine of 30, sine of theta is a half. We did use these two angles, 30 and 150, and we didn't get a half. Yeah, we did indeed get a half. But we have more angles. If I tell you that our sine of 390 degrees is equal to a half, it's equal to a positive a half. It is
second revolution.
Positive a half. So where does this next angle of theta come from? Remember, sine of theta is cyclic. So homeboy repeating himself every 360 degrees. Yeah, every 360 degrees, he's repeating himself. So in my first revolution, I'll get my first set of solutions. Yeah. In my second revolution, I'm going to get my second set of solutions. So we just state in the second revolution, theta will be equal to 360 degrees plus each angle I obtained in my first revolution. The first angle I obtained is 30 degrees. That's where we get the 390 degrees from. And the second angle I obtained will be 360 degrees plus 150 degrees, which is equal to 3 and 1 is 4 and 1 is 5, 510 degrees. And I can check it, sine of 510 supposed to give me positive a half. It does indeed give me positive a half. I mean, I could go in the third revolution again, and I could do the same thing. In the third revolution, theta is 360 degrees plus the angle I got in my second revolution, which is 390 degrees. Notice I didn't add back the 30. I didn't, right? I just keep adding 360 degrees to each previous solution. And this will be equal to 3 and 3 is 6 and 1 is 7, 750 degrees. And by all means, sine of 750 is indeed a half. Yeah? I could go in the fourth revolution. I could go in the fifth revolution, the sixth, the seventh, the eighth, the ninth, and I can keep getting answers. Where do I stop? That's the question. And we figure out where we stop when we do a little more examples. So let me try another one here, right? Let's say calculate theta if cosine of theta is equal to negative root 3 over 2. Okay, first thing you ask yourself in every trigonometric equation, what is cosine theta, what is sine theta, or what is tan theta? In the first case, we ask ourselves and we get sine theta is positive. So that gives us the indication where the angles lie or where my solutions lie with respect to my quadrants. Down here, I'm asking myself, well, I'm seeing cosine theta is negative. So where's cosine theta negative? Well, it's negative everywhere else other than being positive. Yeah? So I know all school teachers' costs, I know cosine is positive here and here. So therefore, cosine is going to be negative here and here. All right? So that is where I'm looking for solutions in my second and my third quadrant. Same principle as before. Calculate your principal value first. My principal value is equal to cosine inverse the modulus of minus root 3 over 2, which is cosine inverse of root 3 over 2. So when I check that on my calculator, cosine inverse of root 3 on 2 of root 3 divided by 2, I get 30 degrees. Now, I'm not going to put theta is equal to principal value is equal to 30 degrees because theta is not in the first quadrant. Theta is in the second and the third quadrant. So that's where theta is going to lie. Theta is equal to 180 degrees minus the principal value, which is 180 degrees minus 30 degrees, which is 150 degrees. And then theta is 180 degrees plus the principal value, which is 180 degrees plus 30 degrees, which is 210 degrees. Again, this is in my first revolution. I will go in the second revolution and see what's going on. In the second revolution, theta is equal to 360 degrees plus whatever angle I got in the first revolution, which is 150. 3 and 1 is 4, 1 is 5, that is 510 degrees. And theta is equal to 360 degrees plus 210 degrees. 3, 4, 5, that is 570 degrees. Now again, I could go in the third revolution, I could go in the fourth revolution, I could go in the fifth revolution, and I could keep going on and on and on. Where do I stop? As this question stands, the question has no restrictions attached to it. It has none. When you get a question in exams, you will get a restriction attached to it. And the restrictions, they look something like this. 0 is less than or equal to theta is less than or equal to 360 degrees, generally. Now, this restriction is called a domain. And the domain, it tells us this region where the graph will exist. All right? By all means, sine of theta exists everywhere on the x-axis. Everywhere on the x-axis, sine theta exists. But the domain says, I want the function to exist between these two values. So if I put a restriction onto my domain, a restriction onto my equation, sorry, I am forcing you to have only a few calculations opposed to having an infinite number of calculations. Now, whenever you have a domain attached, you have to keep calculating until you go outside of the domain. All right? You have to keep calculating. So in a case like this, when I have the domain is 0 to 360, I'm looking for angles between 0 and 360 degrees. So as soon as I jump in my second revolution and I show the calculation that here what? theta is also 510 degrees, but it's not in the domain, or it's out of the domain, which means it's not a valid answer for this domain. If, however, the domain changed, and I say, the question says, let the domain be between this and 550 degrees, then by all means, 510 is going to be an answer. It's going to be an answer, but the 570 is not going to be an answer. Yeah? So suppose now they say, well, between the sun, 741 degrees. I have to keep going on and on and on until I go out of the domain. So all I have to do is say, well, you know what? More solutions exist in the third revolution. And in the third revolution, theta is equal to 360 degrees plus the answer I got in my previous revolution, which is 510 degrees, and it's 5, 6, 7, 8, 870 degrees. He is out of the domain. Yeah. So whenever you have a trig ratio going outside, not a ratio, an answer going outside of the given domain, he is no longer a part of the solution. So in the end, you have to write a little solution line. Theta is equal to 150 degrees, 210 degrees, and I'll work with this domain here. 510 degrees, 570 degrees, and that's it. Although 870 degrees is an answer, it is an answer. It is not an answer in this given domain. All right. Good to go so far. Yeah. All right.